My name is Sri Lakshmi. My topic is grid energy demand forecasting. Grid energy demand forecasting is the process of predicting the amount of electricity that consumers will require from the power grid over various future time horizons. Accurate forecasting is critical because electricity must be produced and consumed almost simultaneously. Large scale storage is expensive and limited. Forecast help grid operators balance supply and demand, plan generation schedules, maintain systems stability, avoid blackouts, minimize operating cost, and integrate renewable energy source more effectively. Forecast can cover different timescales: short term, medium term, and long term, each serving different operational and strategic performances. Traditionally, grid forecasting relied on statistical methods like time series models and regression analysis, using historical load data, weather patterns, seasonal trends, and economic indicators. However, as grids have become more complex with the growth of renewable energy, electric vehicles, and smart devices, traditional methods have often proven insufficient. Today, machine learning and deep learning techniques are increasingly employed to improve forecasting accuracy. These AI based models can capture nonlinear relationships between variables and adapt to changing consumption behaviors much better than traditional methods. Short term demand forecasting is especially critical for real time grid management. System operators must ensure there is enough spinning reserve, reserve and generation ramp up capabilities to meet expected fluctuations. Weather is one of the most influential factors as temperature heavily impacts heating and cooling loads. Consequently, grid forecasting models typically integrate weather forecast as key inputs. For example, on hot summer days, on the load curve can spike sharply due to air conditioning use. Models also need to handle sudden demand changes caused by human behavior patterns, such as shifts in activity during public holidays, sports events, or emergencies. Renewable sources, energy sources like solar and wind introduce additional complexity because their generation is highly variable and weather dependent. Therefore, modern demand forecasting systems often net loading forecasting weather, where the forecasted renewable generation is subtracted from the demand forecast to determine the actual burden on controllable resources in high renewable penetration regions. The importance of demand forecasting. Demand forecasting enables utilities to anticipate peak loads and avoid blackouts. It supports efficient generation and planning and reduces the need of excess capacity. Accurate forecast can lead to significant cost savings for both utilities and consumers. Types of demand forecasting. Short term forecasting focuses on predicting demand for hours or days ahead. Medium term forecasting typically covers weekly to monthly predictions. Long term forecasting looks at yearly trends and requires different modeling and approaches. Factors influencing energy demand. Weather conditions such as temperature and humidity have a significant impact on energy usage. Economic factors including GDP, growth, and industrial activity also drive energy demand. Social behavior such as changes in population and lifestyle must be considered. Data sources for forecasting. Historical consumption data is fundamental for identifying trends and patterns. Weather data from meteorological services helps adjust forecast based on climatic conditions. Economic indicators and demographic data provide context for future demand trends. Forecasting techniques. Time series analysis is commonly used to forecast energy demand based on historical data. Machine learning techniques such as neural networks offer advanced predictive capabilities. Regression analysis helps in understanding the relation between demand and influencing factors. Time series analysis. Time series analysis identifies patterns over time, such as seasonality and trends. Techniques like auto-regressive integrated moving average are often employed. This method requires careful selection of parameters for optimal forecasting performance. Machine learning in forecasting. Machine learning algorithms can capture complex patterns in large datasets. Techniques like support vector machines and random forest enhance prediction accuracy. These models benefit from continuous learning and adaptation to new data. Regression analysis. Regression analysis helps quantify the impact of various factors on energy demand. It can reveal the strength and direction of relationships between variables. Multiple regression models can include several predictors for more comprehensive insights. Challenges in demand forecasting. Unpredictable weather events can lead to sudden spikes in energy demand. Changes in consumer behavior, such as increased remote work, complicate predictions. Data quality and availability can affect the accuracy of forecasting models. Role of technology. Advanced software tools are essential for processing large data sets efficiency. Smart meters provide real time data that enhances demand forecasting accuracy. Cloud computing allows for scalable storage and processing of forecasting models. Case study. A utility company implemented a machine learning model for demand forecasting. The model improved forecast accuracy by 15%, leading to cost savings. This success led to the adoption of similar technologies across the organization. Case study. Utility company B utilized time series and analysis to manage peak demand. They achieved a 20% reduction in operational cost through better forecasting. The approach allowed for more effective demand response strategies. Integration with renewable energy resources. Demand forecasting is critical for integrating renewable energy into the grid. Accurate predictions help manage the variability of solar and wind energy. This integration supports a smoother transition to a low carbon energy future. Regulatory frameworks. Governments often mandate utilities to conduct demand forecasting for grid stability. Regulatory frameworks can incentive accurate forecasting practices. Compliance with regulation ensures reliability and consumer protection in energy markets. Future trends in forecasting. Artificial intelligence and big data are set to revolutionize energy demand forecasting. Enhanced predictive analytics will lead to smarter grid management systems. The rise of IoT devices will provide unprecedented data for real time forecasting. Policy implementations. Policymakers must support research and development in forecast technologies. Investment in infrastructure for data collection and analysis are necessary. Collaboration between public and private sectors can enhance forecasting capabilities. Finally, grid demand forecasting is no longer a one-time or periodic activity. Thanks for real-time data availability and edge computing, many grid operations are moving towards continuous forecasting where models are constantly updated with new data and continuously adjust their predictions. This dynamic forecasting capability allows grids to more flexible, responsive, and efficient, ultimately supporting a more resilient and sustainable energy infrastructure. AI models are being developed to predict both the demand and the likely generation dispatch curve. which types of plants will be activated so that utilities and regulators can manage grid decarbonization strategies more efficiently. Grid energy demand forecasting is essential for reliable and efficient energy systems. Continuous advancements in technology will improve forecasting accuracy. The collaborative approach will ensure the successful integration of renewable sources. Forecasting models must evolve to be more localized and granular, moving from centralized bulk load forecasting to neighborhood or even building level predictions. Title. Thank you for your attention and I welcome any questions. Feel a list of case studies and publications on energy demand forecasting can be found. Academic journals offer in-depth analysis, forecasting methodologies, and case studies. Thank you.